Hello and welcome back to Math Class in Session. Continuing, applications of calculus to problems involving exponential functions. So we've developed calculus procedures and algorithms for finding rates of change and intervals of increase and decrease and critical points, and for sketching curves and finding maximums and minimums. And all we're doing here is a couple of word problems which are increasing our repertoire of functions that we can deal with while we do these procedures. An example from medicine. The liver gradually breaks down any drug injected into the body. Suppose the concentration of the injected drug is given by C of t equals 10 times t times e to the negative 0.01 t, where C is the concentration of the drug in the bloodstream in milligrams per liter and t is the time after the injection in minutes. Determine the rate of change of the concentration of the drug in the patient's blood at time t. The key words there being rate of change. Well, that means we have to differentiate. So we'll take our function, and I put brackets around the two factors to emphasize the fact that all we're looking at here is a product, and we have to use the product rule. So the derivative is, of course, a product rule. So we'll go first thing prime times the second thing plus the second thing prime times the first thing, which is carefully done here. First thing prime times the second thing plus the second thing primed. It's a copy times the derivative of the exponent times the first thing. And we can factor out, which is a usual and normal occurrence, e to some exponent. So let's factor out e to the negative 0.01 t out of each of these two terms, and we end up with this expression. The expression represents the rate of change of concentration in the blood for the injected drug. And there's your rate of change there. It's the derivative. Continuing, when did the maximum concentration occur, and what was the maximum concentration? Okay, so I brought forward both the function and the derivative, and we're asked for a maximum. Looking for a maximum means we'll have to differentiate it, which we did, set it equal to 0, and solve. Well, setting it equal to 0 is going to be fairly easy to do once it's factored, because e to the I don't care what is never 0, so this factor must equal 0. So we'll set that factor equal to 0 and solve for t. Now we know the critical number for the function. Let's put it onto a prime line. And let's note this prime line starts at 0 because we don't have any negative time here. This is starting at 0 when the drug was injected. Time was 0, and from there it just goes on. And we have a critical number at t equals 100. Evaluating the intervals is fairly simple to do. I've evaluated them as positive and negative, and I suggest you confirm that those two intervals evaluate to positive and negative. And now this appears that we have a maximum when t equals 100. And we're interested in what that maximum is, so we'll take the 100 and substitute it into the c of t expression. We'll achieve c of 100 by plugging in and doing the math, and what we have is 1,000 over e, which is about 367.9. And now we can make our final statement. The maximum concentration in the blood occurs at 100 minutes and is about 367.9 milligrams per liter. Example 2, another application from physics, an elementary physics question. The distance fallen for a person free falling from an airplane while skydiving is given by an equation. D for distance. T is in seconds. D is the distance fallen in meters, and T is the time of the fall in seconds. And there it is in front of you. Determine the equations for velocity and acceleration. So it's the the normal procedures to find velocity and acceleration, we'll have to differentiate. So we'll take our d equation and differentiate it carefully. So let's check. This term differentiates to 57.65. To differentiate this term, copy it times the derivative of the exponent on e. And tidying it up by multiplying the two constant factors together gives us this. The velocity at time t. And for acceleration, let's differentiate the velocity. And when you do that, we can just drop the first term, copy this term that has the e in it, there's the copy of it, times the derivative of the exponent. And now we can multiply the two constant factors together, and that gives us a of t. Acceleration at a given time is 9.8 times e to the negative 0.17 t. This is a positive number because we're measuring the distance from the plane, not from the ground. Bringing the two equations forward for velocity and acceleration, calculate the velocity and acceleration of the skydiver at several points in her fall, at the start of her fall, after 20 seconds, and after 40 seconds. Well, at the start of her fall, t will be 0, so the velocity will be 0. And the acceleration, if t is 0, we see that it will be e to the 0, which is 1 times 9.8. So our acceleration, when t is 0, will be 9.8 meters per second per second. The velocity at 20 seconds, we'll take 20 and substitute it in here for v and do the math. And v at 20 is 55.7 meters per second, while the acceleration at that time, taking 20 and subbing it in for t, turns out to be just 0.33 meters per second per second. So the acceleration has certainly dissipated from 9.8 meters per second all the way down to 0.33 in just the 20 seconds. And for 40 seconds, v of 40, plugging in 40 into the v equation, right there for t, so plugging in 40. Doing the math carefully, 40 times negative 0.17 is negative 6.8. Doing the math on a calculator, we get v of 40 is 57.6 meters per second, while a of 40, the result of subbing in 40 into the a equation, still getting negative 6.8 when we go 40 times negative 0.17. Doing the math on a calculator, the acceleration at 40 seconds is 0.01 meters per second per second. And from this we can see algebraically that as time starts at 0 and proceeds forward, the velocity starts at 0 and then v of 20, it's speeded up to 55.7, and at v of 40, it hasn't speeded up much more, only up to 57.6. While acceleration has started off at 9.8 and has dissipated quickly to 0.33, all the way down to 0.01 meters per second per second. We can see that as t grows larger, a of t diminishes, and it actually approaches 0. And if we can sense this by subbing in a large number here, and we can see that what happens is it will be 9.8. This will be on the denominator, and it will be a large number on the denominator, and 9.8 divided by a large number is 0. Similarly with velocity, as t becomes large, a large number appears on the denominator of this term, so this term will become 0, so v of t is approaching a terminal velocity of 57.65 meters per second. If the parachute deploys after 20 seconds, so the person pulls the ripcord after, say, 20 seconds, not too long of a ride when you think about it. 20 seconds is not that long, although I'm sure it would seem kind of long when you're falling through the air. Well, not falling through the air, just hovering in the air with the earth hurtling upwards at you. And the minimum height at this time must be 1,000 meters. What is the minimum height for the airplane when the skydiver jumps? The minimum height. So what's the minimum height to have a 20-second free fall if you need 1,000 meters cushion between the time you pull the ripcord and the time the chute opens? Solution. The minimum height must be the distance fallen in 20 seconds plus the extra 1,000 meters. Let's call this distance height minimum. The distance is, brought forward the formula for distance, so height minimum must be d of 20 plus 1,000. The math is pretty simple. You sub in 20 for t and evaluate it on a calculator. For this jump, the minimum height would be 2,164.3 meters, and that's about 7,100 feet, which is quite a ways up there. A small plane can reach that easily, but from the ground, the small plane would be just a tiny speck.